Welcome to the CERIAS seminar series for April 18th. Today we have with us Merjan Topkara. Merjan is a graduate student here at Purdue, expecting to complete her PhD in the next few months. She has her undergraduate degree from Purdue University in 2000 and has been here right here in 2001, and has an extensive publication record in various aspects of computer security, but we'll be talking to us today about issues in integrity, and in particular integrity of natural language text.
Thank you very much for the introduction. I'm Merjan Topkara. I'm a PhD candidate here. I will tell you about a topic that probably you didn't hear much of before. It's about natural language watermarking. For example, we are living in a digital age, and this is a typical page from internet, and you see a lot of objects on this page: an image, a video, a text, audio. You can even get the audio. And the other part that we are very much interested in is your say. This part. You can put your content on the internet now, and it's pretty easy. But the trouble we have is, how can you have the control when people are reusing your content? When it is being distributed, you lose your control over the intellectual property of this. So we have to come up with a way so that the digital content property protection of the owner is provided for text as well as other things on the internet. Before going into details, I really want to acknowledge my collaborators. I have closely collaborated with Professor Atala from Computer Science, Professor Dab from ECE, Purdue, Dilek Hakkani from University of Berkeley, Victor Raskin from Computational Linguistics at Purdue, Giuseppe Riccardi from University of Trento, Cüneyt Taşkıran from Motorola Labs, and Umut Topkar here from Purdue. And I have also collaborated with Shirini Bangalore from AT&T Labs and Owen Rambo from Columbia. And you can as well reach to these people if you have any other questions about this work. Our problem is controlling how the information we create is distributed or reused, as I have mentioned. So how can you be sure your emails are not being reused? For example, you have put time to write an email that has a very meaningful, important content, or a blog, or a wiki edit, and you don't know whether people are using it. Or even your articles, whether they are being published in another conference by other people. Also, there is another aspect of it. As a reader, how can you trust an email you're receiving from your bank that is really from your bank? And so we need a rights protection system that travels with the content. When we say travel with the content, is different from digital signatures. When you remove something from when you open the digital signature, you can copy and paste the text. The problem with text is it is very easy to copy and paste, use it partially, insert in it. It is different from image or audio. Even non-tech savvy users can do that, like copy paste the text. Our approach to this problem was information hiding, which I will tell you more about. So I have assumed that my talk will be all assuming that you have no background about anything that I'm talking about. So I will be going through as fast as I can through the required background. The first thing is information hiding. It has two main branches: watermarking and steganography. Steganography probably you heard of. It means hidden writing. It is based on covert communication. So you see here an Arctic hare on the top. It's pretty white for this display, but that Arctic hare in fact carries the picture of that jet plane in it. So it is a steganography where people are just sending the picture of Arctic hare image, but they're also sending the picture of that jet plane. And it is a typical image that you can receive as a forward from one of your friends. So steganography deals with how you can perform this covert communication, and also steg analysis, how you can detect that there is a covert communication going on. Watermarking, which I will focus more in this talk, is about content protection, as I have said. There can be several types of it. A typical example is a visible watermarking example that you see. That small icon has the IBM logo in it as a visible watermark. You can see it if you look at it very carefully. The other type of it is invisible, which is much more robust because it uses several techniques from signal processing. You can also try to do a fragile watermark. For example, you wrote a document, you don't want people tamper with it, or you want to detect if it is tampered and deny that I'm not the owner of it, somebody tampered with it. And the other type is the robust watermarking. You can use it for fingerprinting, metadata binding, copyright protection. We'll talk more about this. What is natural language watermarking? It is a way to enable copyright holders to enforce their intellectual property ownership on text, which I have been telling you more about. But here there is another detail we need to discuss. What is the value of the text? Because I want to preserve the value of the text while I'm embedding your copyright information into text. So throughout this work, we have defined the value of text as meaning, grammaticality, and style. So, for example, meaning is important for not disturbing the communication. Grammaticality is as well. Style is a different issue where the author really wants to preserve his style while you're embedding the information. So we want to mark the text such that we do not reduce the text value. Also, the adversary is forced to reduce the text value when he wants to undo our embedding, when he wants to remove the watermark. Why do we need natural language watermarking? One thing is that I have been telling you, authenticating the source of the document. The other is proving or denying of the ownership of a document or controlling the distribution. There are several applications of digital watermarking, like digital libraries, online newspapers, or stores. And the last bullet tells about the typical watermarking applications like content protection, text auditing. This is a very simple example. It's in fact a mock-up example because it is very hard to achieve this with a system, which we will be talking in more details. So the top sentence you see is from the abstract of this talk. It is the original one. And later we have a key, which is a secret key, and a message. Here, another principle we follow in watermarking is Kerckhoffs's principle. We don't have obscurity, security through obscurity. The only thing that is hidden is the secret key. Using this key and the message, I want to change the top text into another text so that it carries the message. I can do several changes. One of them is paraphrasing the first part of the text, where I say one of the main sources of knowledge acquirement is the internet, instead of the internet has become one of the main sources of knowledge. I can insert new words like witches, or I can do synonym substitution, but the challenge here is how to perform this fully automatically, not without using any human intervention, which we will discuss in more details. One of the traditional challenges we have compared to other watermarking schemes, like for images or audio, is the low bandwidth. Most of the documents are short. For example, if I insert only one bit into one sentence, if I'm talking about an email, for example, it has 10 sentences, 10 bits of information might not be enough to prove your case in a court. So, and the other thing is, even if I have 10 sentences, I might not be able to change all of them. Because, for example, here I put up an example, like, I run by the river every morning. I want to insert some information in it. For example, I can try to, my system automatically can think that it's a passive sentence. And it can try to rewrite it as, the river run me every morning. It is grammatical, but it's meaningless. Or I can do synonym substitution. I can change run into manage. I manage by the river every morning. It is not meaningful. The other thing is the last sentence. It is grammatical, it is meaningful, but it is not very common. Like, the author might not want to say, I don't not run by the river every morning. Another challenge we have is the powerful adversary. He can automatically edit individual sentences. He can permute the sentence order, which is very hard to do in an image without being noticed, or can delete or insert new sentences. Here, sentences, I mean the units that I'm using for embedding information and detecting it. And also, he has access to the same data and software resources that I have used for watermarking. So, what Yeah, this is another background slide that I added here. In order to perform this watermarking automatically, we use natural language processing tools. This is a research area under computer science, under computational linguistics, or even in like electrical engineering. Natural language processing aims to design algorithms that will analyze, understand, and if necessary, generate natural language automatically. And there are many electronic data resources available online, like a corpora, for example, Wall Street Journal text, or corpus. Corpus means a long text that is a representative of a language. There are many electronic dictionaries like WordNet or VerbNet, or off-the-shelf parsers, generators, machine translation tools can be used to create a watermarking system. I will tell you a little bit about the previous approaches. There are two different ways of performing information hiding into natural language text. One way is you can generate the cover text. It is usually used for steganography because the text doesn't have any value. So you give me a message, and I just generate a spam email, like in the case of Spam Mimic. If you go to spammimic.org, you type in your message and it creates a spam email for you. And you can send it to your friend. It will look like a spam email sent by you, but in fact it has a message inside it. But the other case that we deal in watermarking is modifying a cover text, which is a little bit harder because we have an active adversary who wants to remove our watermark or insert his watermark on top of our watermark. These techniques that are proposed for given cover text can also be used for steganography as well because you're inserting a message. This is a steganography example. I told you about Spam Mimic. This is a very classic example. So this is by Warner, proposed in '92. What you do is this is the message. If you can see my mouse, this is the message we want to insert, and this is a probabilistic context-free grammar. Every rule in the grammar has a special code. And what we do is we start from the beginning and try to insert this rule and generate a sentence at the end. Insert this message and generate a sentence at the end. So we start with the S rule and we look for one. Here. And we go with the rule that is using SCB, and then we need to insert the sequence that is starting with 0, 1. So we go for C and we pick everybody B because it is the 0 encoding, and we continue this until we fill in all the we put in all the message and we get the sentence everybody wants pie. This is what is behind the Spam Mimic tool. Another work from natural language watermarking. In fact, this work is coming from Purdue. Here, there are two approaches that is proposed in order to perform sentence-level watermarking. The first approach was using a syntactic parser, create a syntactic parse tree of a sentence, which you can see here. Ned loves Jody. This is a tree, in fact, you can use the parentheses to create the leaves. And the system proposed by Professor Atala and Professor Askin here and a group of students, we want to change the tree so that the encoding, the bit string that we will assign to the nodes of the tree changes. And the reader later will assign the same labels to the tree and read the bit string to detect the message, to extract the message out of it. Same idea was used in the second work, the semantic-based one, but the tree was different here. It was the text meaning representation. You're using the semantic parse tree of the sentence, which is here you see the parse tree of this sentence, and here the transformations are semantic, meaning-based transformations. This tool is more powerful than the first one because if you change the meaning of the text, without, in fact, changing the full meaning of the text, it can even survive through translations. In fact, I was part of this work when I came here in my first year. You cannot really see, but we published a paper. It's okay. The black is not. So there are a couple of names here, probably recognizable to you. We published a paper at Information Hiding Workshop in 2002 that is about the semantic based watermarking. I'll tell you more about our recent approaches. You can provide resilience to remove attacks in two ways. One of them is really using obscurity. You are hiding the information carriers through the sea of many sentences. For that, we propose sentence-level watermarking, or you can make it really hard to undo the embedding changes for the attacker. And that one is the second and the third work that I will tell you about. The system that, like, we name our system as Enigmark. This is based on linguistic transformations that are defined over a sentence. I'm paraphrasing a sentence, for example. I'm not looking at information carriers at the word level, but I'm looking at them at the sentence level. Because we wanted to use the sentences because it provides a large feature space, and we need a larger feature space because our watermarking algorithm is based on orthogonal features. We want the features that we used for selecting who will be the information carrier be orthogonal to the features that we are using for embedding. For example, my system picked this sentence because it has the words frank and close. For some reason, it was looking for this for the selection, but I can rewrite this as this chapter will be closed by this frank discussion, and my embedding feature would be the number of prepositions in the sentence, which I change by doing this transformation. Or I can change it in another way. When I say this chapter by this frank discussion will be closed, I even change the number of punctuation, the commas in this sentence. So the selection is still there. So the reader will be able to find this sentence, and later the reader will be able to find the embedding features. As I have told you, we need two types of features. The first type is robust features. We want our selection to stay there. So for this fact, we use the robust features for selections, and we want them hard to be undone by the attacker. For that, we are now currently using like words or the verb classes. The yielding features are the ones that are easy to change. For that, we are using them for embedding the watermark bits. And again, like this work appeared in a paper at ACM Multimedia Content Protection recently, in fact, last year. And you can see details of it here. This is a very small snapshot to show you like a little bit more detail about it. This is a system that like we have built. It is using Xtag parser is an outside tool, outside resource, WordNet and RealPro for generation. And the middle ones are like the ones that we have developed. So given this sentence at the top, he said Canada and Britain recently rejected the idea, this system can automatically rewrite it as he said the idea was recently rejected by Canada and Britain. Let's move on to the other ones, the other systems that we have developed. Here, our aim is to make it hard to undo the embedding changes. We have used the hiding virtues of ambiguity. So when you speak ambiguous, people can get different meanings from what you have said. So we wanted to lower the adversary's power. So we thought if we increase the adversary's uncertainty about the original text, we can achieve this lowering the power of adversary. And please keep in mind that we assume that the adversary is a machine, not a human reading the text. Because at that point, our systems assume that the adversary has spent the time to rewrite the text. And we have used knowledge asymmetry between the embedding process and the adversary. For example, like this is a term that I learned in the US, Go boilers. And it can come from like any of the synonyms of Go. It can be belong boilers, it can be survive boilers, it can even be die boilers, because it is the same in the same synonym set of Go. So it is harder for a person who is hearing Go boilers to decide where it came from. So we are depending on this knowledge asymmetry. And we call these type of transformations computationally asymmetric transformations, where performing the transformation one way is easier, but when you want to reverse it, you need a disproportionately larger computational resource or a human intervention. And we use robust synonym substitution, which is one of the computational asymmetric transformations. For example, I'm given the sentence, the robot is very smart. The meaning is very clear here, but if I change it to the robot is very bright, the attacker is confused. Is the robot polished or smart? Because in its database, it thinks that they are both the synonyms of the word bright. Again, this appeared in a paper that you can find details at ACM Multimedia Security. I want to tell you again a little bit about what is behind this echo mark system. What we do is we build a graph out of a given electronic dictionary, say WordNet. The graph is the words and the senses. Sense means a meaning, and every word can have several nodes in this graph if it has more than one meaning. And later we assign weights to the edges of this graph. The weight is the similarity between two words. So I want to know the similarity between go and survive versus go and die, for example. And later, out of this graph, we select a subgraph using our secret key. So it is harder for the adversary to figure out what we have used for embedding. And also I color this graph, the small graph, with 3 colors because I have 3 roles for every word. One of them is carrying the bit 0 or bit 1, or maybe it can be non-encoding. And also I have to also deal with some constraints. The other constraint I have is, given a synonym set, given a word, I want to have equal probability for embedding 1 or 0. So I want to divide its synonym set into equal number of 0 carriers and equal number of 1s. So the coloring has to take care of this constraint too. Another thing we wanted to achieve here was quantifying the distortion. As I have told you, the author might say, okay, I don't care if you can embed 5 bits, it's enough for me, please don't change too much. And he can set a lower threshold for distortion, because when I am replacing, I'm putting in some distortion to the text. Also, another distortion we want to quantify is when an adversary wants to undo our changes, I want to maximize his expected distortion. As I have said, we want to embed the watermark so that the adversary will reduce the value of the text when he's trying to change it. So what happens is, when there are more than one alternative to insert 1 bit, we pick the one that is staying below the author's threshold, the embedding threshold, and maximizing the expected distortion of the adversary. And I will give you an example of how we do it. Let's say I want to replace the word operate, and both go and run can insert the bit that I want. Let's say it's 1. You see here the weights, and for simplification, every synonym is just 1 distance from its synonym. So every one in the same set is just 1 distance. The edge weight is 1. But we don't care about when we are quantifying the adversary's distortion, we care about the distances of the candidate. If I pick run, for example, my candidates will be, for the adversary will be move, escape, or operate including. I want it for him to be hard to find that my original word was operate. I want to increase his uncertainty about what was the original word. And given these distances and the number of neighbors, our candidate is run instead of go to replace operate with, because it will make it harder for the adversaries to come back to operate. And this is another system that we have built. Here the aim is we are moving into another field now. Here all this talk I have been talking about grammatical text, the text that has high value, the text that has style. But the daily exchange text does not have those properties. It's a cursory text. Mainly you write email, when you're writing emails or SMS, you don't care whether it is grammatical. If you can pass that, hey, meet me at 6 p.m., that's enough for you. You don't care whether there's a typo in that message. So this creates another channel for information hiding, because typos can occur in any part of this document, and usually humans adapted to these errors, and they can really perform very good spell correction. So we can use these changes to embed information. In fact, it is not only typos. As you can see some examples on the bottom. The first example is a typo, but the other one is an acronym that people use very commonly. It stands either for lots of love or lots of love, or the lead speak, if you know, every character has another matching in the lead speaks. This is also something very commonly used, or the smileys, or the colloquial language. And even DCT, it means discrete cosine transform in one area, or divine command theory in theology, I think, as far as I know. So what we did was, the challenge we had was powerful spell checker. So I have inserted errors in my text to insert my message, but then a spell checker can come and, hey, this is wrong, and can ask the author to fix it, or automatically can fix it and remove my watermark or my steganographic message. So what we decided to use was using ambiguous or stealthy typos, or both of them together. What I mean by an ambiguous typo is, for example, I'm given the word world, and I want to change it to a typo of it. I can pick world, which is very close to wood, word, and world. In fact, I picked them from Microsoft Word. If you write it this way, at least my version, gives all three options. It doesn't even give which one is more probable. It just gives them equally probably a fix of the typo world, which is an ambiguous typo, which will confuse the adversary. The other typo that we need for an active adversary in the case of watermarking is a stealthy typo. For example, I can receive this sentence in an email, don't forget to bring the cake. I can change it into sake, which is a dictionary word, and which is totally meaningful. But since I know the communication between me and my friend, I will be able to figure out, hey, I'm bringing the cake, like it's not the sake. And this is impossible for a spell checker to catch. Unless they're using some language models, unless they know the communication between me and my friend. Another thing that we have not implemented yet, but it's a area that we can go in. There are two-way ambiguity in these documents. For example, GBH stands for Great Big Hug, grievous body harm, which is totally different meanings. Or you can rewrite good to see you in 4 different ways that I have seen, in fact, more ways. Another way for ambiguity. And this system also lets us apply some heuristics when we want to increase the ambiguity of the attacker, the adversary. We can either maximize the adversary's uncertainty about the original word, where we use the entropy. So if the candidate word has a higher number of synonyms, like the example that I have given you, it's better for us because it will be harder for the adversary to come back, as you have seen in the example. But I can do another thing. I want to maximize the probability that if the adversary randomly changes some of the words to their synonyms or to their typos, he will stay on the same bit. So he has replaced by my bit carrier, which was carrying 1, with a synonym. But if it is still carrying 1, he didn't really do any damage to my watermark. This work also appeared as a paper at SPY 2007. Okay, so I want to mention a few things that I have told you about and some of the impact of this work. I have presented to you 3 different approaches which are equally powerful and which have assumed different scenarios. The first one is Enigmark, the sentence level watermarking one. The second one is EchoMark, which is using robust synonym substitution. And the third one that you have heard is Marker, which is ambiguous errors that you embed into cursory text. We have covered several types of text, like short text, long text, edited text, or cursory text throughout this work. And also we have, I wasn't able to give you too much details, but one of the concerns we had was a light mark detection process. Because there is this thing about watermarking. If you watermark an image, a photograph that you have taken, when you put it online, how will you be able to find that somebody else has put it on their web page? You need, for example, Digmark uses robots that are going around, checking every image and trying to figure out if there's a watermark on it. So the detection process needs to be light so that these robots can go around without disturbing the communication of other people and figure out whether there's a watermark on the displayed image and that the domain of that image is not your domain. You don't own that domain. So we need all these systems take into account that the detection, the watermark extraction is a light process. This is a challenging problem. As I have told you, there are many challenges included because we are working on text, and also there are many challenges involved in information hiding. There are a lot of application areas for this. You can, as I have said, you can try to watermark your emails, or you can try to watermark your articles. And there are many applications why you want to do that. And Another thing that we have done is we have increased the interest in the research area. So we are known as a Purdue group who is dealing in natural language watermarking, but there are many people who who have started to work on natural watermarking because we have been publishing, we have been sending people like emails about this conferences where they can publish. And as a future work, we want to work on the applications where we have a system that uses natural language watermarking to deal with a problem that the system has. We want to improve the evaluation technique. So when I create a marked document, what is the distortion that I have inflicted on it from the original document? Or was I successfully successful in providing robustness against attacks? Like attacks is also benchmarking is another thing that we have to work on. Also, large-scale user study. We want people to read the document and say, oh yeah, it's meaningful and your watermark created, like instead of just the machines. The watermark document is very meaningful and doesn't disturb my reading. Or we want to increase the capacity and the resilience. We want to also try different languages. We have been working on English because English has, there are many tools available for English and different genres, like different types of documents like novels. That's all. Are there any questions?
Questions? I have one. This trade-off between meaning, introducing ambiguity,
Can you use the mic?
Where this trade-off with meaning, so that you're introducing ambiguity into the document in order to fool the adversary, but hopefully not fool the intended recipient. Presupposes that you know a lot about the communication anyway. But do you have a clear set of measures for some of these? I mean, what conditions can you assume ambiguity? And what is it? So I mean, I can see various other things. So for example, if you were able to say this document has been modified and that were sufficient, then there would be some other techniques. Do you have a real clear delineation of what are the assumptions that are appropriate in given situations?
Yeah, some of the distortion metrics that we have put also tries to capture that. For example, there can be different similarity metrics that we use. So I have told you about a graph that has the similarities as the weights on the edges. So there can be several similarity metrics that we use to define what is a similar word between two. That is an automatic way. The other way that we are thinking about is a practical way. For example, when I am watermarking the document, I can perform it as the author is typing the document, or I can just perform it before he saves it, and I can ask him, like, I'm planning to replace this word with this and this and this. They are like equally possible for me. Do you like, which one do you like? Or whenever I'm doing a replacement or like changing a sentence into another sentence, I can ask the consent of the author. Because the thing that we have, like the advantage we have is when the author is writing the text, he's there and I can just ask him about it because it is not a time consuming event for him. So he can approve the changes that I do so that I know whether it is disturbing the reader's understanding of the text.
Other questions? Okay, I'd like to thank you.
Thank you.